Yeah, thanks very much for coming. I think it's been a nice meeting so far. I'm going to pick up, as Hisham already indicated, speaking about some of the things that Hisham has already mentioned. There will be a bit of overlap, but I'm aiming for kind of a different aspect. And in fact, I'm trying to give you, for review purposes, a kind of first principles recollection, lightning recollection of the full argument that goes from this hypothesis H, and I'll motivate that again, all the way to this braiding of defect branes. That's the plan anyway. So I'll start with hypothesis H. I'll recall how this induces an M5 brane model on the topological sector at least. I'll recall how, once we know what branes are, the subtlety about how to distinguish kind of solitonic from probe branes mathematically. Then I'll talk about using this, how to find this configuration space that will be the moduli space for defect branes, and I'll focus on this case of M5 intersections on 3 branes on an M5 world volume. In our article that I'm citing here, we discuss in parallel that, and it's type 2A dual, which is type 2B dual, which is intersecting D3, D7 branes. We go in some detail through this match and how, I mentioned this briefly, how what I'm saying on M5s here, when you dualize it back to D7, D3s, it does match a whole lot of folklore or common wisdom of what should happen with strings at ADE singularities. But I'm going to focus on this M5 picture, since this conference is about M theory, and that's what we're supposed to be focusing on, I suppose. I'll explain what the resulting M5 states are, and then indicate as an outlook at the end about the braiding. So just want to highlight maybe one thing before we start here. This conference is of course titled, as you know, M theory and math. Math exists, M theory doesn't exist quite yet. It's actually a working title for a hypothesis, and just to emphasize maybe how this comes about. The big problem of currently available quantum field theory is that it's just perturbative. There's actually no theory, despite of what some people may claim when they say, oh, it's so boring, the standard model is so well known. We do not know why hadrons exist or which properties they have, because then the confined, strongly coupled phase of QCD, for which there's no coherent theory, there's just a web of partial theories, And at the same time, as Hisham already mentioned, also solid state physics, they are expected to be strongly interacting phases whose actual theory is at best ill understood. There's just really no general theory. And so what's the point of string theory really, just to recall? So in string theory, after lots of twists and turns, it started out as being actually kind of in Polyakov's original work, kind of started out as being something like a holographic theory of flux tubes in order to describe the strong coupling sector of QCD, and then the many twists and turns, it came back to this. So now in string theory, you can say, okay, if you have any strongly coupled system, it could be realized as sitting on a brane inside a higher dimensional stringy bulk. But the original problem actually remains that also the string theory is just known currently, perturbatively, and it's, in a way, if you really go to the bottom of it, you have this asymptotic series, which you don't know how to resum. So in the end, it really suffers as such from exactly the same problem that the original perturbative quantum field theory suffered from. You do not know what the full non-perturbative theory is. The big difference, I think, of string theory is that now once you've reformulated your perturbative quantum field theory as a theory of branes, suddenly there's a whole lot of hints. And that's really what people mean when they speak of the second duality revolution, the second superstring revolution. And when people casually talk about, branes and M theory, none of which has an actual theory, we all mean this web of hints that exists, which is tight enough that one can at least imagine that one can say a whole lot of things about this web. But the point really for a conference on math, or for mathematical physicists entering into this, is now to take these hints, these cooking recipes, this web of consistency checks, and turn it into some actual mathematical formalism. And the question was kind of clear, and in the 90s, I think there were still people really attacking this problem, but this has really stagnated, I think one can argue. And I think it's plausible to say the reason it has stagnated is because there was just no idea what we're actually looking for, what the actual mathematical formalism is. What is the actual principle? Like, the problem with constructing M theory is not that it's hard in the sense that, oh, here is what you have to do, and it's just very hard to do. The problem is you don't know what to do. There was no principle. Perturbative string theory has clear principles. The Feynman perturbation series generalized, puff up the Feynman diagrams to worldsheets, that's a clear principle. But what is the principle of M theory? Like, what are we actually looking for that has been quite open. Sorry, sort of catching my breath. And I just want to highlight that this is really what Hisham has been doing like all along, starting some decades back. This was his point, really, in my paraphrase at least. Hisham should correct me if I'm saying this incorrectly, but is to say, okay, given all these algebra topological conditions that we see when talking about M-branes, clearly the theory wants to be just like general relativity, has its underlying mathematical theory, differential geometry. M theory, I mean, that's kind of the original hypothesis 0 there. M theory should have as its underlying theory algebraic topology, like modern algebraic topology. And what we should really do, and what Hisham started to do then with his articles on topological structures in M-branes, is to like scan this web of hints for patterns in all these cohomology classes that appear and say which of these patterns, oh, this will be a recurring problem, which of these patterns are recognizable as some fundamental thing in algebraic topology. Maybe we can recognize sort of the equations of motion in algebraic topology that it wants to be. And the culmination of that development, or at least one strand, the culmination of one strand of this, was the formulation of this hypothesis H. And I want to, since I think it's both actually very, so hypothesis H, I want to claim, once you actually understand its logical ingredients, you should slap your forehead and say, oh yeah, I mean, this is so obvious. It's not this, what I'm trying to convey now is that this is not an outrageous hypothesis. Once you understand maybe how the K-theory hypothesis actually comes about, which is widely accepted, I'm going to call it hypothesis K, just to imply that it's on the same general footing, you'll realize that hypothesis H is something that, whether right or wrong, you do want to check. It's not just, some crazy idea that we dreamed up at some point. It's something that's just there. So let's review how this works. So we should really ask, I was once at a strings conference where somebody actually asked us over dinner. So all these string theorists sitting there having given talks about D-branes all along, and there was this conference speaker saying, you know what, if you want to have a fun conference dinner, just ask your neighbor, what is a D-brane actually? Right, this was string math conference where people were supposed to know this. And of course was hinting at the fact that even such a basic question is generally left unanswered. I mean, this, again, just a web of ideas which is so close that people begin to imagine that they know what a D-brane is, but sort of mathematically. Anyway, so let's ask, what is a brane configuration really? And I'm going to ask this in 3 stages. And so let's see. So if you wish, to a classical asymptotic observer like Faraday would have been Maxwell in the old days, you're sitting on this asymptotic space-time, and you're measuring fluxes going through surfaces or higher dimensional surfaces that you span out. So there's a bunch of forms, which I'm denoting by F here with some indices just running through the degrees and the forms. And you notice then they satisfy sort of what Maxwell would have called 1/2 of his equations of motions. They satisfy differential relations. The differential of any one of these flux forms that you form is, well, in the simplest case, just 0. In the general case that we actually care about, the interacting cases, it's some polynomial in the other forms. And usually there's some filtering here on this. It's just not all other forms, but sort of the previous ones. And so that is kind of what we now call higher Bianchi identities. It's if you wish, the topological half of any set of equations of motion for any higher gauge fields will always be divided, and this is related to the discussion we're having. You always say, okay, it's 1/2 of the equations of motion, which tells us about something cohomological, and the other half will tell us about all the coupling to the dynamical metric. And we're focusing not to do the second step before the first. We're focusing on this first step now. There's no point in saying, oh, we don't know what the theory is, and then somebody makes the first step. People complain, oh, you haven't done the second step. We're doing the second step, but first we should be carefully doing the first step. So this is general Bianchi identities. For Maxwell, this is just df equals 0, and I'll show some other examples, but you all know these examples just a moment. So I'm going to modernize these statements now in order to make progress and say, okay, what does it actually mean to have this system of differential polynomial equations? Well, in modern language, using some causal duality, you realize that this says exactly that the collection of the f's are jointly flat differential forms taking values in a nilpotent L-infinity algebra. You can take these polynomials P and regard them as being the high structure constants of a nilpotent L-infinity algebra, or of a Sullivan model, if you wish. This is really ancient story if you understand that L-infinity algebras are really just one way of talking about rational homotopy theory. That's where this rational aspect comes in. But for physical purposes, it's good to speak of L-infinity algebras here because it fits exactly the same structure in which a flat a non-abelian Lie algebra valued form is a flat non-abelian algebra valued form, maybe with values in this Lie algebra, and we can do the same thing with L infinity algebra. So we can sum this up, these Bianchi identities, by saying, okay, if you hand me any set of Bianchi identities, I say, okay, this is your L infinity algebra that controls the flux forms, the curvature forms. And so what I should do now, as a semi-classical observer, if you wish, this is Dirac's perspective. We're still looking at classical background fields, but he made it semi-classical in the sense that he said, well, what, as you all know, what if a quantum particle, an electron, propagates in this background? Dirac, with his Dirac strings, right, really observed that even if you have just these classical background fluxes, if you want to couple them to quantum branes, in his case a zero brane, there's consistency conditions, charge quantization conditions, which he understood are just related to the fact that there should be, if there are, that's really the argument. He really realized if there are branes, zero branes, namely what he called the magnet, or what for his case would be the magnetic monopole, there should be some unit of them. They should appear in units, and that's what the computation shows of Dirac's charge quantization. And in modernized form, highly modernized form, this is not how Dirac stated it, we can understand this as follows. If you take any nilpotent L infinity algebra, this is really the fundamental theorem of DG algebraic rational homotopy theory. Any finite rank nilpotent L infinity algebra arises as the white-hat L infinity algebra of a space, of a topological space. This is shown here in the next line. So I'm not explaining how this works, but it's just a fact. And yeah, I should say all this is later, what I'm saying here is all described in great detail in this monograph that is now in print, which Hisham and I have written, the character map in non-abelian cohomology, where you can find all these details. But much of this is classical. It's not always presented in this application to flux quantization that I'm applying here. Anyway, so the statement is, for any nilpotent finite type L infinity algebra, there's a topological space, a classifying space. In fact, there are many that has that L infinity algebra as its, so there's a way to extract L infinity algebras from topological spaces. It's something like, in a precise sense, that was actually Sullivan's original motivation, it's in a precise sense the infinitesimal version of the loop group of that space. That's why Sullivan's original article was called Infinitesimal Methods in Homotopy Theory. And given that space, we can regard it as a classifying space for a cohomology theory. So you all know, I guess, that ordinary cohomology with, say, integer coefficients is the same thing, or can be computed equivalently using classifying space by mapping into the Eilenberg-MacLane space called KZN, which is the space that classifies this cohomology theory. This turns out to be, by statements known as Brown representability, or related statements, quite general, and it actually generalizes to non-abelian theories. So we can speak about spectra. We don't have to speak about spectra. We can just take any topological space A and declare that the homotopy class of maps into it are the cohomology classes in a cohomology theory. If A is an Eilenberg-MacLane space, this is ordinary cohomology. If A is a space of Fredholm operators, this is K theory. If A is a sphere, this is cohomotopy. We'll come to that. But it just works very generally. So in this picture, cocycles are really just maps to the classifying space, and coboundaries are homotopies between these maps. That's kind of how homotopy theory really interplays with algebraic topology, which in the end makes really these two sides of the same subject. So there's something using this, that's what we describe in this book in quite some detail, but it's, I think, intuitively quite clear. We can now form a non-abelian de Rham cohomology of L infinity algebra valued forms. Well, the description is easy. Cocycles are these L infinity algebra valued forms, flat, which I equivalently can write as DG algebra homomorphisms from the Chevalier-Eilenberg algebra, that's the CE here, of that L infinity algebra to the forms. But that's just a way of writing it mathematically. So the cocycles are these systems of Bianchi identities satisfying fluxes, and coboundaries are concordances between them. That gives a non-abelian generalization of de Rham cohomology, which reduces to ordinary de Rham cohomology in the case that your L infinity algebra is just concentrated in 1 degree on a single generator and is hence the classifying L infinity algebra for ordinary de Rham cohomology. And so here's the point now. This thing that you know as the Dixmuir-Douady class for ordinary cohomology, or as the Chern character for K cohomology theory, that construction exists quite generally. We call it the character map in non-abelian cohomology. It's, if you wish, the Chern character generalized from K theory to any A cohomology theory, to any generalized cohomology theory. And that is a construction, is really rationalization at the bottom, but on the level of cohomology, it's the thing, or it's a construction that systematically takes cocycles in this A cohomology, which are subject to lots of homotopical constraints due to the fact that A can be a non-trivial topological space and is in general. Takes that to this non-abelian de Rham cohomology, which is still quite rich, but much less so. It's a rational, quite purely differential form version. So this character takes A cohomology classes to such systems of flux densities satisfying Bianchi identities. So that means whenever you see a set of Bianchi identities, you can, and Dirac tells you should ask, well, are they actually the Chern character, or the generalized character, of a non-trivial A cohomology class? And making that choice, remember there's a choice in choosing A here. There are infinitely many A's that have the same rational image. So there's a choice involved here. Making that choice is the same thing, if we go back to Dirac, is making a flux quantization, is proposing a flux quantization law. So, yes? No, I'm not assuming a product. It's in general just a set, actually. So in general, non-abelian cohomology just forms a set. As you know already from the ordinary degree 1 non-abelian cohomology, which just maps to BG. If G is non-abelian, you just have a cohomology set. That was Chern's original construction, actually. So this non-abelian, that's the whole point really of non-abelian cohomology, that you say, well, wait a second, just to speak about cohomology, we don't need suspension isomorphisms, we don't necessarily need abelian group structure. That is nice if we have it, but we can speak, and Chern, way back, over 100 years back, did speak about cohomology classes much more generally. And that's what we do, and it may seem outrageous at the beginning, if you haven't seen the non-abelian examples yet, but it follows precisely the same pattern and is a sensible generalization. The character exists on these non-abelian theories. On BG, the Chern character is essentially Chern's original Chern-Weyl map. And so you can think of what we're doing here in this sense is taking the original theory of non-abelian principal bundles, hence of non-abelian Young-Mills fields, if you wish, and boosting that up to higher fields. So we're asking, what if the fields of M theory are not just plain Young-Mills fields, as they're clearly not, is there some higher analog? And we're saying, well, yeah, take any non-abelian cohomology theory that might be in a higher analog. So the naming. Right, is that map which universally approximates, so this is what we call the character, is the thing that universally approximates any cohomology theory by rational cohomology, by the corresponding rational cohomology. For K theory, it reduces to the Chern character. And yeah, we have this debate with the editor. Should we call the generalization of this a Chern character? Or it's not really. I mean, Chern wouldn't have recognized it probably, but anyway, this thing exists. It's exactly what you want, a charge quantization, what you want for a charge quantization law. It's the mechanism that approximates torsion data with rational differential form data. You want to ask, well, is there a general mechanism? Yeah, there is. It's called rationalization, homotopy theory, and on generalized cohomology, it's that character map. And then just to highlight, just to flash this, I'm not going to use this much, but just to highlight, once you've chosen the charge quantization law A this way, so for Dirac would have chosen integral cohomology, or, Minasi and Moore, Wittenberg would have chosen, you of course would have chosen K theory for charge quantize the d-brane charges. Once you've done this, the general formalism tells you how to produce the modular stake. I'm calling it A hat here, following some tradition of the corresponding gauge potential, right? So far we had just the fluxes. Once you've chosen the charge quantization law, there's a mathematical procedure then to tell you what is the local gauge potentials, the vector potentials in Maxwell theory. It's given by this famous homotopy pullback that Hisham already mentioned briefly. You effectively pair the characteristic, the charges, which are given by maps to A, with these flux forms, which are given by maps to the sheaf, as it were now, of flat de Rham-Bellite forms, and you kind of say, well, let's enforce the constraint that these should have the same image in real non-abelian cohomology, which is really just a way of saying these fluxes must satisfy these charges. Okay, let's have a question. Yeah, I think that's a misconception. That I know that parts of the community want to say this, but this will give the moduli stack of actual gauge fields. I mean, clearly these are the things, the propagating. I mean, previously we cared about the propagating degrees of freedom, like in Maxwell theory. That's where the degrees of freedom propagate. So for instance,
really where my question was, that the data.
Yeah. See, we're talking about M theory, and I'm just going for the obvious thing. There's a C field in M theory, and there's its dual. And I'm just telling you how that field will arise. We started talking about just the fluxes with G4, but of course, for instance, the coupling to the membrane is the C field that appears. I'll come to this actually in a moment. So this is just standard stuff about how fields, gauge fields, high gauge fields, or as they're now sometimes called continuous higher form symmetries, arise. So there's this general construction. I'm not going to focus much in this talk. I just want to say this is there once you choose the flux quantization law. And what I will focus on, I'm mentioning this mainly to bring home the following point. So in this stacky language, which is kind of in the background now, you've heard me say this word now a few times, even though I'm not going to explain it here. It's described in much detail in this book. But you can now, since this is so A hat now is the moduli stack for your fields, charge quantized under A, you can ask, well, what if I don't just look at single homotopy class of maps into it, which will be kind of the fields, but what if I take the mapping stack? So you remember, as it's indicated here, not just the maps, but also the homotopies between the maps. So these homotopies now translate into the gauge transformations, the higher gauge transformations between these things, and I haven't drawn it here, but then there's higher order homotopies of homotopies. To the higher order gauge transformations, we have an n order gauge field. It will have corresponding tower of higher order gauge transformations. And so this thing is really an integrated version of what in usual physics literature would be the BRC complex, where these higher order gauge transformations are just remembered infinitesimally in terms of these ghost fields. This is the thing that knows everything about all the fields, globally defined. Actually, that's why I'm calling it the integrated in the sense of globalized. It's not just a local construction. It knows about all the Dirac strings and flux quantization laws and about the gauge transformation between them. And it is, that's the point I want to make, of course, maybe there's some discussion here. This is on shell for that half of the equations of motions which we're currently looking at, which is that half which the flux quantization, which the Bianchi identities capture, the first half of Maxwell's equations, if you wish. It is on shell for that, since our cohomology theory imposes these equations of motion. So in that sense, we can think of it as being the on-shell BRC complex. And we're postponing in this construction, and this has been discussed a few times now, we're postponing the coupling to the dynamical metric. We have a few articles that do discuss this. It's also super exceptional in the title, but I'm going to ignore this at this point. As Hisham amplified, what we're doing here, since we're just asking what is branes, in the nature of branes, as we saw from Dirac, their counting and their charge nature is all in this cohomological sector of the equations of motion. That's what I'm focusing on here. That's the first step. So since it's the on-shell BRC complex, remember how it goes in ordinary quantization non-perturbatively. Many people, let me amplify this because I'm not sure, so we're talking about RG flows here. There's a very good example to keep in mind if you want to ask, well, what does it actually mean to the non-perturbative quantization of any field theory? The good example to keep in mind is Chern-Simons theory. You construct the classical phase space, which is Chern-Simons, is a space of flat connections, and then you ask for a pre-quantum line bundle over this, so some bundle of classifying spaces of cohomology theories, and then you take the polarized sections of that bundle. So if you reformulate this as, I think Mattei also did at some point maybe. Anyway, some people noticed long ago, mathematicians noticed that this prescription of geometric quantization, which gives you the non-perturbative quantization of your system, that's all non-perturbative Chern-Simons is quantized, it's a cohomological operation. What we're really doing is we're looking at a bundle of spectra over phase space and taking the sections of that. Or if you do this for K theory, you can rephrase it as computing an index. Anyway, so what we're going to ask is we're going to say, once we've chosen our flux quantization law, sort of in this half topological sector of our theory, then the quantum states of that theory will be, after some choice of line bundle of spectra, tau over this BRST on shell BST integrated complex, will be the tau twisted cohomology, which is just the sections of this bundle. So that's what I'm going to do in a stripped down version, which I'm going to show. We're going to see, after I've charge quantized the fields of M theory this way, we're going to say, well, let's look at this moduli space of its fields and compute its cohomology and see if this gives a sensible notion of quantum states of M branes. And my point will be that at least in the examples we're looking at, that will be quite the case. Just to, yes, please. Yeah, that's a very good question. I haven't talked about the polarization. We're going to look at these mapping stacks, mostly just the underlying topological space, but they're kind of discrete, just having the higher structure, so that there's no polarization to be chosen. It's just the topological theory. But in fact, in the case that I'm going to end up on, where this is the configuration, where this mapping stack will be given by the configuration of points, configuration space of points, that carries a canonical holomorphic structure. And since it's a Stein manifold, the twisted cohomology that we're going to compute of it is actually equivalently the holomorphic cohomology. So it is actually, at the same time, the space of holomorphic and hence polarized sections. But that is a very good point. That is certainly a subtlety that needs more attention here. I'm kind of looking at an example here where it's either solved by itself or not so relevant. But this is something we'll have to discuss in general. What the polarized sections are, yes. So that is the story that sets us up. That I think, or we claim, right? This is now really what we say. This should be your starting point. If you want to ask what is non-perturbative any higher gauge theory, that's what you need to do. Write down the flux laws, choose a flux quantization law, form the corresponding differential cohomology theory, form the mapping stack. That's your phase space now, the sort of half topological sector. And you somehow find the right pre-quantum bundle over this, and its twisted cohomology, that's your quantum states. That's the prescription. That's what gives non-perturbative Chern-Simons theory. So some of the quest now is do this for M theory. And just want to highlight, this is really just a recap. Everything again, maybe I can be very quick here. To Hisham's point that all of this is twisted, we're going to be concerned with not just with one brane species, but with intersecting such species that each have fluxes that talk to each other. You know this from the D-NS branes, where the NS string ends on the D branes. And this, if you go through it, eventually says that the Bianchi identities of the R forms actually twisted by the flux forms of the NS string and the NS5 brane, which just means really that the differentials now of our fluxes are polynomials in the original fluxes and in some H's which have been flux pointers before. And the upshot is that, again, rational multiple theory kicks in. You can say, well, this is now a parametrized L-infinity algebra. This actually turns out to be the rational approximation, not just to a single space A, but to a fibration of A spaces over some classifying space, which I'm calling B curly G here. And then, so this twists everything. And then this is what Grotnik would have called the relative picture. Anything you do in algebraic topology, where you map, you can always ask, well, what if everything is sliced over some parameter space? Everything depends on that. And that's what this situation is. So where previously we said an ordinary cohomology theory, a general, like ordinary in the a non-twisted generalized non-linear cohomology theory is about homotopy class of maps from our domain into the classifying space A. Now we take a twist on X, which is a map to this base space BG, and we look at homotopy class of maps sort of over this twist up to homotopy as shown in this picture. And then the Chern character, or this generalized character, generalizes to this point of view. Now we have twisted A cohomology on the left, and the Chern character takes it to a certain twisted non-abelian de Rham cohomology on the right, which again produces these flux forms. And there's a corresponding, here's the de Rham cohomology. It's the same picture. We slice everything, and now it's time to finally look at the examples here. So I'm calling this hypothesis K now. K is for K theory. This is the standard thing that you all know from the 90s, but I'm just calling it that way to highlight that this is what this hypothesis H is meant to be an M-theoretic analog of. So just to recap how the original motivation for hypothesis K went. I mean, it's not quite that made quite that explicit in the literature, but if you look at the original Muminasian article, that's really what they do. They observe that, look, the Chern character in K theory has this form. Well, which form does it have? So let's take KU0 to be any classifying space for complex K theory. Could be the space of Fredholm operators that Hisham mentioned. Could be the usual B stable U. And BU1 canonically acts on this. So that's this group P, homotopy equivalent to this group PUH, acts on this in a way that Hisham actually flashed. So you have this vibration of spaces, and you can ask, what is the Chern character? What does this rationalization map send it to? Well, it sends it to an L-infinity algebra, which produces fluxes of exactly the form that are known to be the Bianchi identities of the RR and NS fields. So it says there's all these RR field strengths F. If the differential is not closed, so it doesn't vanish, but it's the previous flux wedged by the H flux. And that was kind of the first ingredient, and then Witten said, oh, you know what? People said, okay, this smells of K theory, and then Witten came up with this, how should I say, heuristic argument. They said, oh, that actually makes sense, because if we imagine that we put some D-branes, super D-branes, and the anti-branes next to each other with the chain patent bundles, then what we expect, this was of course just an expectation, what we expect the tachyon condensation to do, it's supposed to take all chain patent vector bundles that we have here with their virtual anti-bundles and annihilate them to the extent that they annihilate. And he said, oh, isn't that curious? That is exactly the equivalence relation by which one obtains topological K theory on a compact Hausdorff space. So that was the kind of the non-perturbative argument to choose this quantization law, right? You've seen that the fluxes are of the form that the Chern character of K theory would give, but there could be an infinite, or there is an infinite number of, unstable theories like K theory that have the same Chern character. So why do we focus on K theory? Well, we say, okay, it does seem to capture brane anti-brane annihilation in its after we've charge quantized, and so here's what we do. Hisham already showed this. We just say, well, let's just play the exact same game now for the M-theory fluxes. What is the Bianchi identities for the M2, M5 brane? It's this here. Unfortunately, I haven't boxed them. Hisham has showed it, of course. DG4 equals 0. And then there's this nonlinear coupling term. And of course, I have the worst of typos here. So of course, DG7 is proportional to G4 squared. So this is the analog of the Bianchi identities that we just saw for K theory. So very obvious question. That's what Hisham asked answered in 2013 is, well, independent of anything, but let's just, if you see these, you just saw the K theory story. We want to ask, what is the cohomology theory whose Chern character, whose generalized character, imposes these fluxes? And again, there's an infinite choice, but there's again one obvious one, as there was for K theory, and that is cohomotopy. You can take the old article by Sullivan from the 80s and look up the rational model for the spheres. The even-dimensional spheres have exactly this kind of quadratic coupling, and exactly for the four sphere, it's exactly that coupling. So if you take the cohomology theory that is represented by the four sphere, this is something that Pontryagin discussed way back in the 1920s. He published about it only a little later, but he understood back then already. He was trying to compute homotopy groups of spheres, and he realized that for that it's actually sometimes useful to what is called map into a sphere, which he really defined cohomotopy at this stage. So that is an ancient non-abelian cohomology theory, which hasn't found, I think, due attention as such, is in this general scheme, that cohomology theory was classifying spaces or homotopy type of any sphere, in this case a four sphere. And so the statement of this character map is, using Sullivan models, I mean, this uses ancient ingredients, but maybe it hasn't been put into this perspective before. The theory that is classified by the four sphere, the cohomology theory, is exactly that which is that canonical choice which enforces the flux quantization law that you see for M2, M4, M5 branes. And then you can again ask, well, is this twisted in some way? We don't expect there to be other branes, but actually the M2, M5 do couple to the kind of non-dynamical gravity, namely to the topology of the tangent bundle in a very crucial and very subtle way. And well, for some of the spheres, for a finite number of exceptional cases, spheres do arise as coset spaces of Lie groups acting on each other, of one group being acted on by a subgroup. And specifically, S4 is the coset of, is a coset of sp2, which is spin 5. But in this context, it turns out to be really important to realize it as sp2. So the compact, you may know this as the compact symplectic group. It's the quaternionic unitary group, quotient by sp1 times sp1, which is of course su2. So that means, given that it has this coset formulation, it canonically sits, I scrolled over this. It canonically sits in a fibration over BSP2, the classifying space of sp2, with fibers being S4. So this now tells you there's canonically a version of sp2 twisted cohomotopy. And first, maybe the first big consistency check one now runs into, which we work on in this original article, M theory, anomaly cancellation on 8 manifolds, is that you check, well, what is that? Suppose we twist this way. So suppose we ask that spacetime, that M theory is on an 8 manifold, R2, 1 say some 8 manifold, and we ask that we use the corresponding sp2 twist and compute cohomotopy charges. What conditions does this? What is the flux quantization on the forms? And it turns out among a long list that Hisham flashed among a long list of quantization conditions, one find this enigmatic witness-shifted flux quantization law, which says that it turns out that the G4 flux that we started quantizing is not actually itself representative of a class and integral cohomology, right? It's a form, but you can still ask, does it have integral periods? It does not. But if you shift it by something else that also doesn't have integral periods, namely the fourth fraction of the first point, so the first, so 1/2 of P1 does have integral periods since we're on a spin manifold, but 1/4 again doesn't, but the sum turns out to be. So this is a famous argument by Witten that he made in 2 articles on the M5 brane partition function, and it led actually quite remarkably Hopkins and Singer to write their article, Quadratic Functions in M Theory and Differential Cohomology, to start the machinery of differential cohomology theory, because they said, we need to find a cohomology theory that enforces this funny flux quantization law. And they built something that they argued does this. But here, in just quantizing in cohomotopy theory, that just comes out. That's one of the first of a long list of things that come out. And I'm not going to go through this, but we checked a whole lot of things that seem to say that at least this cohomotopy cannot be far from what actually quantizes charges. There's some wiggle room here. One could, for instance, we find that, I come to this maybe very briefly, if you want to describe heterotic M theory with some background flux gauge fields, then you need to slightly modify actually the force. You can modify the force here by going to lifting it through its Penrose vibration to the twistor space. So there's, but this does certainly capture something. And so that's where the hypothesis H comes about. It just says, well, okay, let's just run with it. Well, let's just check this now, really. So this may be wrong, right? But I'm hoping if you follow the argument, then even if this is wrong, this is something you want to check. You want to say, oh, yeah, this needs to be checked. This is something that deserves just at least a fraction of the attention that the K-theory conjecture got, because it's at least as plausible. I think it has actually more detailed checks now regarding, but anyway, so both hypothesis H and hypothesis K can be wrong, but they cannot be wrong by much. They by construction fit the rational differential form flux structure. They fit the brane anti-brane annihilation picture. Yeah, I'll come to this for the cohomotopy case. And they fit, yes? Yeah, that's exactly what this pullback was that previously you said we didn't need. That pullback produces, if you treat an A being Ku, then this homotopy pullback produces differential Ku. It's the Hopkins-Singer model in that case. That's exactly the homotopy pullback that they looked at. That produced the Hopkins-Singer model of Ku. If you feed in cohomotopy there, you get the Hopkins-Singer version of unstable cohomotopy. refinement. But yeah, that's exactly the point. That all of this is canonically differentially refined, even though it takes work to extract what all the information in the homotopy pullback actually is. And yeah, you see this comes out. So it turns out that, where was it here? So it turns out that the differential of the G7 receives, with the twisting, when you couple it to the background field, the P1 and P2, the Poynerian classes of the background manifold, they interact with both the fields. They quantize, shift quantize the charge of G4, and they impose, they make this IA term up to the shifts appear in G7. And we'll see this in a moment. This turns out to fill what I think was a major gap in the literature. This will make the M2 brane charge, because G7, G7 is essentially up to, some correction, which we'll see in a moment. Just like G4 is the charge, measures the flux that is sourced by background 5 branes, G7 is the thing that measures the flux sourced by M2 branes, and called the page charge. And what was completely open in the literature, I think, and we proved it, was that there was no reason why the page charge should actually be integral. There was no mathematical reason to see that there's actually an integral number of M2 branes. And we'll see that one consequence of this charge quantization in twisted comotopies that will actually make the page charge integral. That's actually my next slide, so let me come to this. So I want to speak about the resulting M5 brane model here, by which I will just mean kind of just the coupling to it, I want to discuss the analog of the sigma model of the charged zero brane, if you wish, which has a kinetic term coupling to the metric that I'm just disregarding here because I don't like it. It's because I'm disregarding it here for the purpose of this discussion. And then kind of the subtle topological term in the sigma model of the charged zero brane is its coupling to the background gauge field, which, it's subtle, but it's of course well understood now. You first charge quantize your background gauge field following Dirac by promoting it to a co-cycle in differential ordinary cohomology, which is again our pullback square here. So that is this Hopkins-Singer construction, which now produces Whitehead B2Z. That is the notation of the differential cohomology theory underlying, its underlying charges are in second integral cohomology. That is just ordinary, if you wish, Deligne cohomology, Shiga-Simons characters, or just line bundles with connections. And so, so the kind of subtle part of the action functional in the zero brane propagating on a background of such charge quantized fields is the map that takes a curve, so a sigma model field, a map from a one-dimensional manifold. Do you see? Yeah. A one-dimensional manifold to a target space, takes it to, so this is just notation for the, just kind of primitive notation, right, for the holonomy. So the thing is, with an A1, if you have an A1 form, you can locally integrate it, but since A1 is not in general globally defined, you need to do some Czech cohomology to make a globally defined holonomy, and kind of putting the hat on A1 is what does this, and so I'm just writing it like this. This is supposed to be the holonomy of the line bundle connection of the bundle. So what we're asking now is, can we, for the 5 brane, do the analogous construction? This is kind of an orthogonal consistency condition to which many of the people in the audience, maybe including Christian, have been focusing on finding this. Anyway, this is the global question we can ask. Do we have a well-defined Hopf-Wersomino term on the 5 brane? That's what it's called, actually. The analog of this coupling is the analog of the, it's a certain 7 class on the 5 brane. So anyway, so just to recall how the general machine now works, since we just saw that after imposing hypothesis H, during the charge quantization of the C field, in cohomotopy, the shift G4 plus minus, I guess I'm changing my convention here, this may be a typo, but it doesn't matter, it's integral either way. Since the shifted combination of G4 is now integral, we can form this homotopy pullback. It does now satisfy charge quantization law, and so there's a corresponding differential cohomology theory here, which in traditional text you will find being discussed as being 2 gerbs with whatever that's called, curving and connection data. It's or degree 4 Deligne cohomology, any of these things. And once you have that, again, you get a well-defined version of the coupling of the M2 brane to the background C field, to the background potential. Again, by the same kind of this formula, which is a stand-in for the prescription to actually compute higher holonomies of gerbs over surfaces. So we're asking now, do we have something like this for the 5 brane? And it turns out, investigating this, we need to decompose the Hopf vibration, the quaternion Hopf vibration. See, the point now is that contrary to what happens in much of the literature, the single S4, by the fact that it has this character map involving both G4 and G7, it knows both about the M5 brane charge and about the M2 brane charge at once. It knows both about G7, which measures the M2 brane charge, and G4, which measures the M5 brane charge. So if you just want to talk about just the M5 brane, we have to do, what is it called in math, the Postnikov decomposition. We have to kind of extract that sector of S4, if you wish, which is actually responsible for the 5 brane in the background of the M2 branes. And yeah, a long story short, there's a famous vibration, of course. Over S4 sits the 7 sphere in a higher dimensional generalization of the complex Hopf vibration that you all know, where S3 sits over S2 with S1 fibers in sort of analogous way, replacing the complex numbers by the quaternions. S7 sits over S4 with S3 fibers. And we can ask, given a bulk space-time, charge quantized, M-theoretic space-time charge quantized in twisted 4 homotopy, what if on some subworld volume, which we should actually take to be the ambient MK6 in which the M5 brane sits. So suppose we have some 7 manifold sitting in there. What if on that 7 manifold, so this is supposed to be sort of the sigma model map of this MK6 sitting in X here, containing the M5, we can ask to lift our homotopy co-cycle through the quaternion Hopf vibration. So the subtlety, of course, is you need to work out, as we did, that the quaternion Hopf vibration actually passes to this twisting. It's actually equivariant under SP2. So ignore this middle piece in the middle. You can homotopy quotient everything by SP2. So this gives a vibration also of homotopy of twisted cohomology theories. And interestingly, you find that this lift is precisely what encodes the expected higher gauge field background structure that is supposed to appear in 70 supergravity and on the 5 brane, namely the H3 field. Why does an H3 field appear? Well, you can see it from the Hopf vibration. The fiber is S3. So locally, since S7 to S4 is a locally trivial vibration, locally this lift is just a map to S3, which is the typical fiber. And so we find that hypothesis H, interestingly, after we assume that the bulk fields are quantized in 4 homotopy, tells us that the fields on the 5 brane world volume 3-form field is quantized in 3 homotopy, in the form of twisted 3 homotopy, twisted by this diagram. And then, lo and behold, turns out there is an integral class on, so there is an integral universal class. You can ask, well, given such a lift, can I produce a closed 7 form so that I can do the corresponding background field coupling of the M5? And lo and behold, there is. You can form this combination here, which is which is the term that you know from the Hopf invariant. It is really a twisted version of the Hopf invariant on the 7 sphere. You wedge H3 with this shifted G4, and you add G7, and that is an integral class. And so once we have that, we can play the same game that we did before, and we suddenly know that there is actually a well-defined Hopf-Westominor term on the M5 brane. You might say, you should say, actually, this lift through 7 cohomotopy actually cancels the potential anomaly which would have arisen had this term not been integral, which is a term that has received a little bit, but almost no attention in the literature. There's one article by Kenneth Intriligator from, I forget, the beginning of the 2000s, where he at least asked this question, is this term integral? And then he answered he discussed the G7 term and makes some arguments for the remainder. So he was at least seeing that this needs to be discussed. So this, if you wish, that's the title of our article, is the level quantization. This is the analog of the integrality, say, of the Chern-Simons functional in 3D. And so this exists. I'm skipping over some technicalities here. And I'm just flashing this, because I'm not going to go into this over time anyway already. I just want to amplify that I just showed you the first stages of this diagram here, which became also the logo of this conference. What I just explained is that if we are on an 8-dimensional M-theory space-time and we charge quantize our C field, then the 5 brane is given by these lifts. And by just systematically analyzing the homotopy theory that is encoded just by this quaternionic twisted Hopf vibration, forming this diagram, which may look wild, but we walk through it in very small stages in this article, having a focus on each of the different parts. There's just kind of a higher twisted Postnikov analysis of this diagram. We form certain fibers, look at the fibers. You find a whole lot of structure that is expected on the 5 brane, which is why we thought this might be a fun logo for the conference. I don't want to talk about this, but in this article, this is called the commodity implies twisted string structure MM5. We walk through this in some detail. Much detail, I think. And there's a heterotic version, which I'm skipping over. And the upshot is just the following, is that this indicates that hypothesis H is going in the right direction. So I just want to take this now. I'm not going to talk about the M5 brane sigma model further. I just want to say, okay, let's assume that M2 M5 brane charge is quantized in homotopy. What else? What are some integral statements that we can make now? That's what I want to do. And I guess, Tisha, what's my time? I'm using way too much time, right? Okay. Right. I see. So I'm running out of time. Yeah. Okay, let me go with 10 minutes. I'll try. So now, let's forget all these flux forms for a second. Let's just do some algebraic topology. So we know we have brane charges quantized as maps into spheres. So what now? Let's compute some brane charges. The first thing I do want to highlight is, which is the point that's kind of, everybody knows this when you tell them about it or ask them about it, but sometimes even some referees forget this. It's a very basic thing that there's 2 ways of measuring brane charges topologically. There's 2 spheres you can associate with a brane. In a solitonic brane, like Dirac's original monopole, it's solitonic. Fields would diverge at the locus of the single locus of the brane if you included it. So you remove it from space-time, and as a result, a sphere appears, naively speaking, around that monopole, and you can measure flux through that sphere. That's Dirac's charge quantization. That's the flux sourced by singular solitonic black branes. But there's another thing you can do for probe branes that kind of don't disrupt the topology of space-time. And you can ask, what if I have some brane charge here, just by the fact that I'm forcing charges to vanish at infinity? So which really means, what if I have a bump in the field density, in the flux density, without it actually being singular at any point, just a finite bump? And you keep that bump from just diluting itself by saying, okay, it must not, I have, for some reason, I constrain it from not running away to infinity. Then, mathematically speaking, you're measuring charge on what's called the check or 1-point compactification of the transfer space of the brane, which I'm trying to indicate here by the stereographic projection. And then for rectangular branes, which I'm focusing on just for simplicity, this gives another sphere of a different dimension. It has a dimension shift, which is kind of the compactified transverse space. And just to highlight, that I'm not making this up or something, this is very fundamental stuff. You know this for the Maxwell field. Let's just look at this for standard electromagnetic field. The first picture is supposed to indicate to you Dirac's charge quantization. Suppose there were a monopole, a magnetic monopole. You would remove from space an actual 2-sphere up to homotopy would appear around it, and the integral cohomology that we're measuring is the flux through that sphere. So monopoles haven't been measured, so you might say this is, a physicist might say this is hypothetical, but interestingly, exactly the same mechanism for probe branes is observed in superconductors, where the same thing happens. The usual flux quantization in superconductors kind of follows the same argument. You say, well, what if flux pierces not a sphere, but this transverse plane to a strong magnetic field? But since we're in a laboratory, this field will actually drop off someplace. So there's a physical reason to make all fields and charges vanish at infinity, which really means outside your laboratory. And that condition, again, turns topologically since everything at infinity is identified sort of as a 0 point, all fields have to be the same there, namely 0, up to homotopy. And so there's another 2-sphere, and running this argument gives you exactly, this is just standard Maxwell theory, the flux tubes in superconductors. And so in brane language, we would maybe say the first situation is that of a solitonic black brane, possibly, and the other one is that of a probe brane, probe in the sense that it probes space and doesn't disrupt it. And so what I want to do, I want to look at these probe branes, probe 5 branes, which gets us into territory that is hard to analyze with existing machinery. And a key theorem that I want to highlight now is something that was briefly mentioned by Hisham in his talk, is that there is a an ancient theorem going back to Pontryagin, named after Pontryagin and Thom, which tells you kind of exactly how to measure brane charges in homotopy and how to identify them. That's the main point. How to identify them with actual brane world volumes. That construction is known as the Pontryagin-Thom collapse construction. It's usually written in some formula that makes it very hard to realize what is going on physically. This picture that I'm drawing here is supposed to give the nice intuitive picture of what the homotopy with Pontryagin-Thom collapse actually does. Namely, it says, suppose you have a space-time, which is my dashed grid here, and in there we have a submanifold, which is the solid black line. And suppose I've chosen a normal framing, which means that near the brane, I know what it means to go perpendicular in the direction towards the brane. Once you have that, you can send any point that is near the brane to its directed distance. The actual distance scale doesn't matter for this argument. You choose some scale, you send it to its orthogonal distance. That is a point in R to the dimension of the transverse space. And then you say, well, as soon as I'm too far away from the brane so that my tubular neighborhood ends, let's just send everything, let's just suppose we're infinitely far away from the brane. So you're computing, if you wish, asymptotic directed distance to the brane. Meaning in a closed neighborhood is directed distance, and everything is far away, is taken to be at infinity. But that prescription gives you in total a map from a space-time to the corresponding transverse sphere, right, which kind of measures these distances. And by what we said that homotopy is just the cohomology theory represented by maps to the sphere, we've produced from a submanifold with normal framing a classic homotopy. And Pontryagin theorem was that this is actually an isomorphism between the homotopy group that's on the right here and the group of the unstable cobordism cohomology of your manifold for cobordism with normal framing. So it gives you a precise sense in which now charge quantization in homotopy actually realizes the idea that branes, which we started out in kind of abstract way that we just said, oh, we don't know what a brane is, but as we go far away, it has charge, it has flux. Now we're currently actually seeing that if you do charge quantization in homotopy, the sort of actual submanifolds associated with them. And if you look at how this proof works, what is that relation in cobordism cohomology that implements this relation? Well, it means you divide out cobordism. So I'm dividing out, I'm showing here a simple picture where you have this kind of zero brane here in a, of codimension 1 in a one-dimensional space. Its normal framing is a choice of normal vector pointing either up or down in the simple picture. And the cobordism relation in the simple picture just means, well, if we can connect with such a half circle here to another such zero brane, which then necessarily has its, because the cobordism has to satisfy the normal framing, has to have this opposite charge, then they annihilate or can be created either way. So this is, of course, exactly the picture you expect for, like this is what picture I write in Sakai Tsukamoto models for the 8 branes for realizing QCD on brane intersections, exactly this brane-anti-brane picture. Also want to amplify, even though, I guess probably this needs more time, but we're really talking about in like the Pontryagin-Thom isomorphism. Most people discuss, even though Pontryagin originally did develop it for the non-abelian in the non-abelian generality, later Thom and others did it in the stable theory, and that received all the attention, which is why it's not called Pontryagin-Thom. And of course, you can do a whole lot of things once you've stabilized, but really stabilizing the non-abelian theory, the unstable homotopy, means losing exactly the quadratic nonlinear information that motivated us in describing M theory in the first place. So you can, if you want, if you insist, approximate our for homotopy by what's called stable homotopy then, the cohomology theory represented by the sphere spectrum, but it loses a little bit of information. It still retains more than K theory, but it's sort of in between. And so that's usually denoted by a boldface S or something. So there's a abelian cohomology theory, which is a abelian homotopy. And the Pontryagin-Thom theorem still applies there and equates that with stable, what's usually called cobordism cohomology, stable frame cobordism cohomology. And at that point, one can notice this. Of course, some similarity of ingredients now to Waffer's cobordism conjecture, which says something like, I don't know what it says, something like cobordism cohomology is important for understanding quantum gravity effects in M theory. Anyway, here's the cobordism cohomology theory. The punchline I'm trying to make is that stabilizing, or even before stabilizing, cohomotopy, cohomology theory under Pontryagin-Thom is identified with the cobordism cohomology theory. There's also, just briefly mentioning it, there's also an old theorem called the Barrett-Pretty equivalent theorem, which says that the abelian cohomotopy, interestingly enough, is actually a form of K-theory. It's kind of the most, if you wish, the absolute base of K-theory. It's algebraic K-theory of the so-called field with one element, the non-existing field with one element, which really just means that you construct it from the category of finite sets in just the same way that you can construct algebraic K-theory from the category of projective modules of a given algebra. I'm just highlighting this because this shows that classes in a stable cohomotopy satisfy exactly the relation that Witten took to be the second main hint for hypothesis K, right? So where he said, oh look, K-theory enforces exactly the brane anti-brane annihilation condition, and exactly the same is actually true non-linearly for cohomotopy. Well, that was what this little diagram was supposed to amplify. And now what should I do? I have probably 2 minutes left. -1. So we've seen how to start quantizing, or how to see what probe branes should be classified by, the cohomotopy of these transverse spheres. Then we want to ask, well, what are intersecting M5 branes classified by? So then you need to impose this boundary condition that fields vanish at infinity in the two different directions. There's a way to do this by doing it in two different directions. And then this marvelous theorem kicks in that Hisha mentioned, the May-Siegel theorem, tells you what is the cohomotopy moduli space of such transverse spheres, which are now lower dimension than the sphere we're mapping into. So there's a subtlety here. You can't, Pointryagin Thom tells you there's no classical brane, but there's kind of now branes hidden in the higher homotopy classes. And yeah, long story short, one finds that the cohomotopy of these transverse spheres of spaces that model intersecting M5 branes are equivalent to configurations of spaces of points in their joint transverse space, which now I exactly identify with the, see, this is the transverse space. So each of the points is a stand-in now for an M5 brane intersection sitting there. Yeah, here's a better picture of this. So this is the picture that comes up by analyzing the cohomotopy modular space of the transverse spaces that model their intersections. We can compute the cohomology. I'm really done in just a second. And another classical, but maybe not so widely appreciated theorem kicks in, which is due to Vashenko and some other people who computed the twisted cohomology of the, right? We said once we have our configuration, once we have our cohomotopy moduli space now, which we just identify with the configuration space of points, our quantum states should be in the twisted cohomology of that space. So that twisted cohomology has been computed, luckily, and it's actually a rather deep theorem. And that turns out to canonically contain, it's slightly larger, and we discussed in our article what this extra information is. It can be related to logarithmic. Anyway, it contains, curiously enough, the space of conformal blocks of the SU2 Chern-Simons theory, which means that, maybe that's a good point to stop here, that if we identify quantum states of brane configurations inside an M-theoretic bulk via hypothesis H, then they get identified with quantum correlators of a conformal field theory on the world volume, right? So we're looking, I was really too quick now and I'm out of time. We're on this M5, intersecting with an M5. We see in the transfer space, so on the first M5, there's this conformal field theory appearing through the cohomology, right, through the quantum states of these branes, which will form the space of conformal blocks. Yeah, and given that, we can braid this around and find actually that defect branes in string M theory under hypothesis H satisfy anion braiding, as was suspected. I forget the reference now, but there was one textbook on exotic branes in string theory. Yeah, it's really bad that I forget the authors now, but we reference it, where they end on a conjectural note. They say, oh, it looks like defect branes, since they have this, the transfer space, they look just like anions. They should be anions. There is now a way to prove this just by following this general law of what does it mean to do a non-perturbative quantization of a high gauge theory once you have chosen a charge quantization law and applying this to the M theory fields. I'll stop here. Thanks for your patience. Sorry for going over time.
There's a microphone on the podium.
Maybe one quick question and then we can take a break.
So do these anions, can I think, so if I think
take 7D supergravity, the topological theory, the Chern-Simon theory, C3 wedge DC3. So this is like the 3D Chern-Simon theory, which has anyons. Can I think of these anyons here as being anyons that I can associate to this C3 wedge DC3?
C3 wedge DC3. You're looking at the 7D Chern-Simon's term
Yeah.
that descends from 11D supergravity to 7D supergravity.
So if I put this on a boundary, there are anyons. There should be anyons in the same sense that the 3D Chern-Simon theory have anyons.
The only thing is this would be abelian. I mean, that term is abelian.
Well, so still, if I have n C3 DC3, that's a non-invertible topological theory, which should be dual to the non-abelian 5 branes in the boundary. So the question stays.
Yeah, I see. Yeah, okay, I see. I don't know. Yeah, that could be. I don't know. One would have to chase. In fact, I'm sort of so I don't have a concrete answer. But of course, the ingredients. If you start with the 11D Chern-Simon's term, that 11D Chern-Simon's term is of course the source of the flux Bianchi identity for G7.
That's
so
right.
that is the thing that gives DG7. So that is the thing that I built into this theory to start with, and then I ran with it. So in one sense or other, this certainly controls the theory. What I don't know, which I guess what you're asking is, if now that I've done this kind of non-perturbative computation, if I also could take the Chern-Simon's term, just compactify it to a 3D Chern-Simon's term on the transverse space, and if the two would coincide. Yeah, that seems plausible. I don't know. That might be something one should.
That would be interesting to work out.
Yeah, that's a good point. Thanks. Yeah.
Okay, due to time constraints, let's thank the speaker again.